The natural base e is an irrational number. That means the number goes on forever and there's no repeating pattern. Its definition is given right here. We can graph this. We can see what the horizontal asymptote would be, and it would be e if we set y equal to this. But e is simply roughly 2.71828, etc. In most cases, we just say it's 2.72. Sometimes we can even just say it's 2.7 because it's good enough for what we're doing. The graphs of y equals a times e to the arc's power are called natural base exponential functions. You have two basic cases. The first one is when r is greater than 0. Then we have an exponential growth function. When r is less than 0, we have a decay function. Let's look at a graph of y equals e to the x power. But first, I think it might help if we look at things we've graphed before. So let's graph f of x equals 2 to the x power. So we have x and y, and we just need a few points. So -1, 0, 1, and 2, just to get the sense of it. So 2 to the 0 power is 1, so we can graph that. 2 to the 1 power gives us 2, and 2 to the second power is 4. 2 to the negative power would be the reciprocal of 2, so that is 1/2. I will also make a graph table for g of x equals 3 to the x power. I will use the same x values. These are the values you should get. And you can go ahead and graph those and connect that curve. And now finally we have h of x equals e to the x power. So first I will set up a table. All right, first e to the 0 power would just be 1. Now what about e to the 1 power? Well, like I said before, e is always that irrational number that's about 2.7. So if you want to think of it as 2.7 when you graph it, then that's where you're going to make the point. So I'm going to write e, but I know it's approximately 2.7. If you want to be more precise, use 2.72, but when you're graphing, 2.7 is good enough. And e to the -1 power will give us 1 over e, which is approximately 0.4. And e to the second power, again for that one, we could use 2.7 or 2.72 to the second power. But e to the second power gives you approximately 7.4. All right, now go ahead and graph those points and connect them. Be as precise as you can be. Use different colors if necessary. So, underline each one to show which color you're using. Here are the 3 graphs you should have. The lowest one here is 2 to the x power. The one in the middle is e to the x power, and the one that's the steepest is 3 to the x power. Notice that they all have one point in common, 0, 1. And e to the x power is always in between 2 to the x and 3 to the x functions. And that makes sense because e is just 2.7, and 2.7 falls between 2 and 3. Notice that 2 to the x and 3 to the x change when you get to the negative side. So on the negative end, 2 to the x is the highest graph, and then 3 to the x is the lowest underneath here, and e to the x is in between them. But again, when you're graphing e to the x power, just e is just a number, and just think of it as what would the graph look like if it was 2.7 to the x power. It's the same as if I said to you graph, something like y equals 9.1 to the x power. If I said y equals pi to the x power, it's just a number raised to a variable. Okay, now let's graph something a little more complicated. So y equals 2 times e to the negative 1/3 x power. Okay, so based on the previous definition, my a here is 2 and my r is negative 1/3. And that is less than 0, so I expect to have an exponential decay graph. Expect something that looks like this. All right, I'm going to make a table. So x, y, and 0 is always easy to substitute. So 2 times e to the negative 1/3 times 0 will just give me 2 times e to the 0 power, which equals 2. So I have a point 0, 2. Next, because I'm dealing with a fraction 1/3, I think 3 is easy to substitute. So go ahead and evaluate that. So I get 2 over e, which is less than 1 because it's 2 divided by 2.7, 2, and you get about 0.7. Again, for graphs, 1 decimal place is enough. You won't be able to tell the difference, between 0.6 and 0.7, usually on the coordinate plane. All right, the next number I'd recommend is negative 3. And go ahead and evaluate that. And I get 2 times e to the 1 power, so that's 2 times, 2.7 is enough for this, so I get the point negative 3, and for the y I get approximately 5.4. If you want more points, you can. I'd recommend substituting negative 6 as well. So negative 6 would give you 2 times e to the 2nd power, which is about 14, and that won't fit on this coordinate plane. So I'm going to go ahead and just graph these 3 points that I have here. And then go ahead and connect the points. If you want precision, you could always add more points. So if you want to substitute something to give you a larger y value, negative 4 would give you 7.6. So adding that point would definitely make the graph a little bit easier. If you want, maybe also substitute 1, but that's your choice. It will just give you a more precise graph. And there's our exponential decay graph for the number e. Here's one a little more complicated. Y equals e raised to the 0.4, open parenthesis, x plus 1, close parenthesis, plus 3. All right, well, you should recognize first that there is an h and k shift here. So h here would be negative 1, which means that the graph is being shifted 1 to the left, and k is 3, which means whatever you get for the first part of the function, it'll be moved up by 3 units. If you want to make this easier, we could take out those values and get the x and y values for something a little bit simpler. So let's do that. That's the simplified version of the function. Notice that there's no plus 1 or plus 3. And now let's make an xy table. These are the values I'm going to go with, from negative 2 to 2. And just use the calculator to substitute all these values in for x. If you don't have a calculator with the number e, then just approximate to 2.72. Here are the values, and now I can make an xy table for the function we want to graph. And I'm going to use all the previous ordered pairs, but for example, if I want to use that -2 over here, I'm going to subtract 1 from it. And when I subtract 1 from it, it'll give me the point -3. For the y value, because the k is 3, I'm just going to add 3. So that gives me 3.4. And I'm going to do that with every single point. So for the next one, my -1 becomes -2. The 0 is -1. The 1 minus 1 is 0. And 2 gives me 1. And all the y's, I'm just going to add 3. This is very helpful if you don't have a calculator and you have to get these values somehow else, or if the graph just looks too complicated. So go ahead and complete this on your own. And now go ahead and graph those points. If you want more points, you could always get them. For example, if you want to add that 2 gives you 6.3, it might give you a better graph, but I could see already from this that this is exponential growth. And you could also add the horizontal asymptote of y equals 3 if you want. And the horizontal asymptote is of course related to the +3 that we have over here. So there's the graph. Earlier we talked about compound interest. And recall that as you increase the number of times interest is compounded, the value increases as well. So a lot was dependent on that value of n. We were able to compound interest yearly, quarterly, monthly, daily, even more often if you want, but it makes the formula very difficult. However, what if you wanted to compound interest every millisecond of second of every minute? And traditionally you wouldn't be able to do that, because if you put a very large number for n, you'd be dividing by infinity. That would give you 0. E allows us to do that. So let's explore how values change depending on how interest is compounded. So suppose $1,000 is owed on a credit card that charges a 20% annual percentage rate, APR. Complete the table for the various ways interest can be compounded. If you know what to do, go ahead and do it. I'm going to show you how to do it for monthly and continuously. So here's monthly. Well, monthly is 12 times a year, so n equals 12. And I also need to make sure I know what r is in the formula. So r is 20%, but we have to write it as 0.20. So now you just go ahead and substitute those values into our compound interest formula. Your initial is 1,000. And because we're only finding the value after 1 year, you would say that t equals 1. Make sure you round to the nearest cent, and you get this value. For 10 years, you just change the 1 to a 10. And after 10 years, the values increase much more. I also want to show you APY, the annual percentage yield. Here's the formula for it. But annual percentage yield takes into account what would be the same annual interest rate that would give you the same end result as the compounded interest rate. So just substitute r and n into that formula. Try it on your own. And I'm going to express it as a percent. So that value goes in here. A lot of times when you look at a credit card, or if you're getting a loan, you'll see an APR given to you and you'll see an APY given to you. So I'll show you what this APY means. Basically, if if you wanted to calculate this value using the APY, you could just say $1,000 times 1.2194 to the 10th power. So I don't have to do all the math that I did before. And that gives you $7,268.79. Compare that number to our previous number. It's about the same, and the reason for the difference is because of the rounding. So if you ever see, let's say, a credit card tells you that it's compounded monthly and it's 20%, well, that's the same as a credit card that charges 21.94% compounded yearly. Okay, here let's look at what happens when interest is compounded continuously. All right, well, for that we have to use this formula. And my principal is P, so that's 1,000. We have that over there. I'll use a lighter highlighter. Okay, so that's the p-value. My rate is still 20%, so that rate is there. And t is whatever time you want to figure it out. So for the first one, t is 1. For the next one, t is going to be 10. So you just go ahead and substitute into the formula and make sure you round off to the nearest cent, hundredth. So we get that for the first one, and then just substitute 10. All right, so this is a 5, but the 6 afterwards is going to cause it to go up. So you get 7389.06. Another way to calculate APY is just look at how much interest you earned in 1 year and divide it by what you started out with. And in this case, it's 22.14. So in other words, having an annual interest of 22.14 is the same as a continuously compounded interest of 20%. Take a look over here, check your answers. And notice that there isn't a huge difference between compounding continually, compounding daily. It's not. It's only, a few cents after 1 year and a few dollars after 10 years, and the APY is not much different. It's 0.1%. So usually when you see a credit card is compounded daily because it just simplifies things a little bit, and there's not much of a difference between daily and continuous compounding. And here's the graph with all those values over 10 years. The top number is when it's compounded continuously. Notice that it's a smooth curve. This one is when it's compounded yearly. So notice that the jumps only happen at 1 year intervals. That's the only time interest is added. And that's the reason it's the lowest, because it doesn't give it as many opportunities for the interest to earn interest.